Real analysis is a branch of mathematical analysis dealing with the real numbers and real-valued functions of a real variable. In particular, it deals with the analytic properties of real functions and sequences, including convergence and limits of sequences of real numbers, the calculus of the real numbers, and continuity, smoothness and related properties of real-valued functions. Scope equals construction of the real numbers equals. There are several ways of defining the real number system as an ordered field. The synthetic approach gives a list of axioms for the real numbers as a complete ordered field. Under the usual axioms of set theory, one can show that these axioms are categorical, in the sense that there is a model for the axioms, and any two such models are isomorphic. Any one of these models must be explicitly constructed, and most of these models are built using the basic properties of the rational number system as an ordered field. These constructions are described in more detail in the main article. Order properties of the real numbers equals. The real numbers have several important lattice theoretic properties that are absent in the complex numbers. Most importantly, the real numbers form an ordered field, in which addition and multiplication preserve positivity. Moreover, the ordering of the real numbers is total, and the real numbers have the least upper bound property. These order theoretic properties led to a number of important results in real analysis, such as the monotone convergence theorem, the intermediate value theorem and the mean value theorem. However, while the results in real analysis are stated for real numbers, many of these results can be generalized to other mathematical objects. In particular, many ideas in functional analysis and operator theory generalize properties of the real numbers. Such generalizations include the theories of Rice spaces and positive operators. Also, mathematicians consider real and imaginary parts of complex sequences, or by pointwise evaluation of operator sequences. Sequences equals. A sequence is usually defined as a function whose domain is a countable totally ordered set, although in many disciplines the domain is restricted, such as to the natural numbers. In real analysis, a sequence is a function from a subset of the natural numbers to the real numbers. In other words, a sequence is a map f, n, n-or. We might identify an equals f, n, for all n or just write an, n-or. Limits equals. A limit is the value that a function or sequence approaches as the input or index approaches some value. Limits are essential to calculus and are used to define continuity, derivatives, and integrals. Continuity equals. A function from the set of real numbers to the real numbers can be represented by a graph in the Cartesian plane. Such a function is continuous if, roughly speaking, the graph is a single unbroken curve with no holes, or jumps. There are several ways to make this intuition mathematically rigorous. These definitions are equivalent to one another, so the most convenient definition can be used to determine whether a given function is continuous or not. In the definitions below, is a function defined on a subset I of the set R of real numbers. This subset I is referred to as the domain of F. Some possible choices include I equals R, the whole set of real numbers, an open interval, or a closed interval. Here, A and B are real numbers. Uniform continuity. If x and y are subsets of the real numbers, a function f, x or y is called uniformly continuous if for all I micron 0 there exists a I0 such that for all x, y and x a y0 there exists I0 such that, for any tagged partition, a, b, with mesh less than I, we have. When the chosen tags give the maximum value of each interval, the Riemann sum becomes an upper Dubut sum, suggesting the close connection between the Riemann integral and the Dubut integral. Lebesgue integration. Lebesgue integration is a mathematical construction that extends the integral to a larger class of functions. It also extends the domains on which these functions can be defined. Distributions equals. Distributions are objects that generalize functions. Distributions make it possible to differentiate functions whose derivatives do not exist in the classical sense. In particular, any locally integrable function has a distributional derivative. Relation to complex analysis equals, Real analysis is an area of analysis that studies concepts such as sequences and their limits, continuity, differentiation, integration and sequences of functions. By definition, real analysis focuses on the real numbers, often including positive and negative infinity to form the extended real line. Real analysis is closely related to complex analysis, which studies broadly the same properties of complex numbers. In complex analysis, it is natural to define differentiation via holomorphic functions, which have a number of useful properties, such as repeated differentiability, expressibility as power series, and satisfying the Cauchy integral formula. In real analysis, it is usually more natural to consider differentiable, smooth, or harmonic functions, which are more widely applicable, but may lack some more powerful properties of holomorphic functions. However, results such as the fundamental theorem of algebra are simpler when expressed in terms of complex numbers. Techniques from the theory of analytic functions of a complex variable are often used in real analysis, such as evaluation of real integrals by residue calculus. Important results include the Bolzano-Weierstrass and Heine-Borel theorems, the intermediate value theorem and mean value theorem, the fundamental theorem of calculus, and the monotone convergence theorem. Various ideas from real analysis can be generalized from real space to general metric spaces, as well as to measure spaces, Banach spaces, and Hilbert spaces. See also, List of real analysis topics, Timescale calculus, a unification of real analysis with calculus of finite differences, real multivariable function, real coordinate space, complex analysis. References. Bibliography, Al Printers, Carol Ambos D. Birkinshaw, Owen. Principles of Real Analysis. Academic. ISBN 0-12-050257-7. Browder, Andrew. Mathematical Analysis, An Introduction. Undergraduate Texts in Mathematics. New York, Springer Verlag. ISBN 0-387-94614-4. Bartle, Robert G. Sherbert, Donald R. Introduction to Real Analysis. New York, John Wiley & Sons. ISBN 0-471-32148-6. Abbott, Stephen. Understanding Analysis. Undergraduate Texts in Mathematics. New York, Springer Verlag. ISBN 0-387-95060-5. Rudin, Walter. Principles of Mathematical Analysis. Walter Rudin's Student Series in Advanced Mathematics. McGraw-Hill. ISBN 978-0-07-054235-8. D'Angelo, Frank. Seafried, Michael. Introductory Real Analysis. Brooks Cole. ISBN 978-0-395-95933-6. Bressoud, David. A Radical Approach to Real Analysis. MAA. ISBN 0-88385-747-2. Kolmogorov, A.N. Fomin, S.V. Introductory Real Analysis. Translated by Richard A. Silverman. Dover Publications. ISBN 0486612260. Retrieved April 2, 2013. External links, How We Got From There to Here, A Story of Real Analysis by Robert Rogers and Eugene Bowman. A First Course in Analysis by Donald Yao, Analysis Web Notes by John Lindsay Orr, Interactive Real Analysis by Bert G. Waxsmith, A First Analysis Course by John O'Connor, Mathematical Analysis I by Elias Zakon, Mathematical Analysis II by Elias Zakon, Trench, William F. Introduction to Real Analysis. Prentice Hall. ISBN 978-0-13-045786-8. Earliest known uses of some of the words of mathematics, calculus and analysis, basic analysis, Introduction to Real Analysis by Jerry Lebel, Topics in Real and Functional Analysis by Gerald Teschl, University of Vienna.